Now we will talk about the flow of two immiscible liquids and the assumptions we are going to take. So let us consider that two immiscible incompressible liquids are flowing in the z direction in a horizontal narrow slit of a length L and width W. The fluid is more dense and more viscous than the fluid 2. Then the fluid 1 will be flowing in the lower portion of the plate and the fluid 2 will be flowing above the fluid 1. We know that if the fluid one is more dense, it will flow in the below portion of the plate. Let's assume that these are the between is the interface, and we have this as the fluid, this thing as we this above part which we have as the fluid 2, and the below part which we have as fluid 1. So we can simply say that the density rho 1 and the density rho 2, the density of rho 1 is greater than the density of rho 2. Why? This is simply because the liquid fluid 1 is heavier. And now we will talk about the assumptions which we are going to take for solving the velocity profile and the flux profile. So the assumptions are: first, we are assuming that the flow is having a steady state condition. The complete flow will be taken during the steady state condition. Second, we will assume that the flow is a laminar flow. Third, we are going to assume that it is an incompressible fluid. Both the fluid which are flowing are incompressible fluids. That is, the density, which is rho 1 and 2 obviously, and the viscosity is constant. Since we are assuming it to be the incompressible fluid, therefore both of these terms should be constant. Fourth, we are going to assume that the flow is a unidirectional flow. By the thing, when we call it as a unidirectional, we need to understand that it's flowing in only one direction. That is, liquid flows only in z direction. Hence, v of x equal to 0 and v of y is equal to 0. Now, the other assumption which we are going to take is Newtonian fluid. We will assume that both of these fluids are Newtonian fluids. 6. Now, we will start with the shell balance. Now, we will consider a shell at a distance of x and a thickness of delta x to start solving the shell balance. Now we will draw the velocity distribution and the flux distribution for these two liquids. First, let us see that what will be the velocity distribution for a single fluid, not double fluid, but just a single fluid. From that, we will extract how we can make a diagram for a double fluid, for how we can make a velocity profile for two immiscible fluids. If we have a single fluid flowing through a slit, then definitely we need to understand, we need know that at the wall the velocity must be zero. So let us draw a straight line here, and then we are assuming that the velocity here at wall is zero. Something, so distance from the wall, it has to be something, and then it keeps on increasing, and at the center we have the highest velocity, and then it goes on decreasing. This is for a single fluid, when we don't have any other fluid, but we just have a single fluid. And similarly, when we make a flux profile for it, then it goes on like this, where it goes on increasing. First it decreases, and then it reaches zero at the center point where the velocity is maximum. We have the flux as zero, and then it goes on increasing and reaches to the maximum level where velocity is 0. This is for a single fluid. So what happens if we have two fluids, both of which are immiscible, and these fluids are flowing through a slit together? So let us make the velocity profile and the flux profile. So yeah, making the velocity profile. Since we have two different fluids, there definitely has to be an interface. Let us assume that the interface is in between, and the upper fluid has a density of rho 2 and viscosity of mu 2, and the lower fluid has a velocity density of rho 1 and viscosity mu 1. We know that rho 1 is greater than rho 2. Also, we know that this is the interface and this distance is b, and this distance is also b. Now we know that this upper fluid, which is the fluid 2, is less dense and less viscous. So we also write a term for viscous, that is mu1 greater than mu2. Now, making the velocity distribution, we first need to understand that these two fluids will have a velocity 0 at the wall of the slit. Why? Because we know that at the walls we have no slip condition, and because of no slip condition we know that the walls are not moving. Walls are at a speed of 0, so any fluid which is passing by touching the wall has to have a 0 velocity at the surface of the wall. So assuming that both of these liquids velocity is increasing after having the distance increased from the wall itself, now we know that the lower fluid has a density higher, so it will definitely have a difficulty in moving. So let's draw the velocity profile for the lower liquid. The velocity of this liquid will keep on increasing till it reaches the middle. This is what we see in a single fluid. But what happens if we have another liquid? Since the upper fluid has a density lower as compared to that of the lower fluid, so it will definitely reach a velocity higher compared to that of the velocity of the fluid with density which is higher. So if we assume that the velocity continues, so definitely there has to be an increase in the velocity, because we know that at the center the velocity has to be same because of no slip condition. So the upper fluid, which is the fluid 2, need to have its velocity increasing, keep on increasing because of lighter density, and we get a velocity profile like this rather than what we got in single fluid. Yeah, so this is our velocity profile. From this, what we understand is that the highest velocity was reached in the fluid 2, rather than we did not reach the highest velocity in fluid 1, but we got the highest velocity in fluid 2. So yeah, we have this line where we got the maximum velocity. Now Making the flux profile, we know that at the point where the velocity is maximum, the flux has to be zero. So let's draw the flux profile. See, so this is the flux profile which we have. Yeah. So yeah. Now we are going to apply a momentum shell balance. So applying shell balance. Why we are applying shell balance? We are applying the shell balance in order to solve the velocity profile and the flux profile for the given case, that is to give case of two immiscible liquids. We know that the shell balance is rate of molecular momentum in across the surface at x minus rate of molecular momentum out across the surface x plus delta x plus external force acting on fluid, which will be equal to 0. Now, writing the shear stress, which is tau of xz at x plus. Now we know that the shear stress is in the x direction because of the velocity z. Since we know that we don't have any velocity in any other direction, we only have velocity in z direction, and the velocity in y and x direction are equal to 0. Therefore, we are only going to have a shear stress at a direction x because of z. Also, we know that the velocity of z is a function of x only and not a function of y and z. Now, writing the shell balance, we can write tau x z x minus tau x z at x plus delta x into WL, which is the area, plus external force acting, which is P naught minus PL by L into WL into delta x is equal to 0. Now, dividing the complete equation with W, dividing this by WL delta x and taking delta x tending to 0, we get tau xz at x minus tau xz at x plus delta x divided by delta x at limit delta x tending to 0 plus p naught minus pl divided by L. From here we can say that we have a definition of differentiation. From that, this we can consider it to be written as del d tau xz divided by dx, which is equal to p naught minus pl divided by L. So this is the equation which we will get after solving this. Now, moving on with the shell balance. On integrating, we get del of tau xz p naught minus pl divided by l integral of dx. From here we can write this as tau of xz is equal to p naught minus pl divided by l x plus c1. So here we get a constant c. We need to solve this constant c in order to get the value of tau xz. From this tau xz we will get the flux profile. So the boundary conditions which we are going to apply for the fluid, so the boundary conditions which we are going to apply for the fluid 1, tau of xz1 is equal to p naught minus pl divided by l x plus c1, that c11, and for fluid 2, tau xz2 is equal to p naught minus pl divided by l x plus c12. So now we have these two constants. In order to solve for these two constants, we know that x equal to 0, we have tau of x z1 is equal to tau of x z2. So yeah, when we are saying that x at x equal to 0, we are having the flux as equal to each other for two different liquids. See, this is the velocity profile and the flux profile. But at this point, assuming that we have this at this point is x equal to 0, the flux for fluid 2 is equal to the flux of fluid 1. So at this point, we do have both flux equal to each other. So at x equal to 0, we are simply writing that at x equal to 0, we have tau xz1 is equal to tau xz2. This, and since x equal to 0, so c1 dash is equal to c2 dash. From this we can claim that c1 2 dash, c1 2. Now we can write, since we know that this is the relation we got, we can substitute this and write tau xz1 is equal to p naught minus pl divided by l into x plus c. Tau xz2 is equal to p naught minus pl divided by l into x plus c.